Hello, in this lecture we begin our study of hardware synthesis. Till now we have seen that at the beginning we have an initial rough idea of the embedded system application that we want to design. The first task is to specify that idea in English language as detailed as possible, as accurately as possible. A specification that that allows us to tell what will be the inputs to the system, what will be the outputs from the system, how will the inputs be transformed to the outputs. So, what will be the actual functionality, that will we will all tell, all these things we will tell in English. And then we have to also tell what are the performance requirements, what are the properties that this embedded system should satisfy, what are its performance requirements in terms of, let us say, the time within which the output should be produced, the energy that it is allowed to consume, the size within which the system has to be built, etc. After we have this English language description of the system, we specify it formally using formal modeling tools. We saw formal computation modeling strategies such as the sequential program model and the finite state machine model, in which the application can be modeled. Now, after this phase, we have a task graph like structure of the entire application, where each task node. So, it is a graph over task nodes, where each task node is a program. For example, the node corresponding, it could be designed at various abstraction levels. For example, we studied HCFSMs and the program state machines, and let us say that each node could be a single program or code in the program state machine, each node. So, that node can, for example, correspond to one node of the task graph at a certain level of granularity. So, if we see this figure, first we have the application or system level, and then after the application of at the application of system level, we have modeled the entire application in terms of a task graph. Now, this task graph, on this task graph we have specifications in terms of its performance requirements, as we told, the cost that it should take, the cost that can be incurred for building this embedded system, and then other properties. Based on that, as we saw, each task node in this task graph will either be built in hardware or software. So, this is called hardware software co-design. So, the entire embedded system application represented in terms of its task graph, and this and within this task graph, each such task will be built either in software and executed as a C program, let us say on a general purpose processor, or we will build a custom or semi custom hardware corresponding to this task node. So, each task node will either be implemented in hardware or software. Now, after we have decided which tasks will be implemented in software, starts the hardware synthesis. Now that we have decided that these tasks will be implemented in hardware, we have to design the hardware and implement it in the form of a chip. So, today we will look at how a specification that we want to implement as hardware will finally be structurally realized in the form of a chip. So, we see that from the application level we have this hardware software co-design, where we partition the system in terms of what is to be implemented in software and hardware, and then for the hardware we first have the architecture level design. In the architecture level design, we have these tasks, a task node which we have to implement in hardware, and this task node is represented in the form of a high level program. or our HCFSM, let us say. And actually essentially what is it? We have a set of concurrently communicating processes. So, each such process is a program. It executes independently and concurrently with other processes, and has interfaces to talk with the other processes and with the outside world. So, if you see this diagram here, B1, B2, B3, B4 are 4 concurrent processes running concurrently with each other, and they can talk with each other through interfaces, and they can also talk with the outside world. Now, this set of programs, this set of concurrently communicating processes will go through a phase called high level synthesis, where it will be transformed in the form of an RTL, or register transfer level specification. And the structure of the register the RTL will have a mathematical specification in terms of what will be the register transfers at each time. We will talk in detail about that, and it will have a structural representation as well in terms of registers, functional units, a controller that controls it, etc., as shown in this elliptical enclosure. Okay. And after this RTL specification is obtained, we go through a process called logic synthesis, in which the RTL specification the register transfers are represented as Boolean equations. We also define the we also define FSMs corresponding to the controller, and then we realize this Boolean equations and FSM controller in the form of gates and flip flops, and that provides us the logic level design. So, this in encapsulation here in this ellipse, we see that we have represented the system that we want to design in terms of gates and flip flops. Now, from this gates and flip flops level design, we go through a process called technology mapping, and we obtain a circuit level specification. From the circuit level specification, this is a transistor level design, and from this we go to the physical level design, in which we obtain the geometrical structure of the circuit on the layout or the layout of the circuit on the silicon wafer. So, once the layout of the circuit, so how these transistor level design will be laid out on the silicon floor will be decided in the physical level design phase. And after this layout has been decided, we go for fabrication of this layout on the silicon chip, and we have a wafer level design, and from that we have a finally packaged chip. Going to a bit more within of this design flow, we see that firstly we have reiterating, firstly we have this application of system level design. The overall problem is expressed through unambiguous specification models, as we just told, and the models includes a C code, which is a representation of sequential program model, sequential process model, and state charts, which is a representation of the HCFSM or hierarchical concurrent FSM models. And the models are essentially have task graph like structure with the tasks with concurrent processes, concurrent communicating processes within them. And that after that we do a hardware software co-design, and the application is broken into threaded concurrent communicating processes, for each of the task nodes that we want to build as hardware. Then the following steps elaborate the design of the hardware components. Now, the hardware design flow goes through a set of phases, as I told. The first one of them was architectural level, and the system is described by its structure and its corresponding functional blocks. So, we have these concurrent communicating processes. Each process is essentially conducts a function, carries out a function, and these are the functional blocks, and each block is essentially a sequential system meaning that it will go time step after time step and conduct a series of operations, and the blocks communicate among themselves. As we also said, the functions to each structural unit is ascribed. We will see how by designing the data path and control path for it, and timing and other constraints are specified on the system. Now, the architectural level specification, we said that we will have we will use models like C and HCFSMs, as we told. The common languages that are used to model this in programs other than C are so from that C specification for hardware, it is most easy to use similar hardware description languages, which like System Verilog, System C, etc. From the C level specification, it is easy to transform them into hardware description languages. Or we could also have a bit higher level called architecture description languages like Lisa, Expression, Mola, etc. At this stage, we can have two types of designs, either synchronous or clocked designs, which we consider them here, or asynchronous or unclocked designs, which we will not consider in this course. Okay. So, from the architectural level, we move to the RTL level, and at the register transfer level, what do we have? The design is composed of a data path and a controller. So, we said that essentially any hardware that we design has a logically structural view. What is its logically structural view? Composed of a data path and a control path and a controller. The data path consists of register banks, functional units, and their interconnections. So, the interconnections will have wires, muxes, demuxes, etc. And a controller. So, what will this data path do? So, data path will transform input data and it will allow certain data in certain ways to be transferred to functional units, get transformed and then stored again back into registers. So, from inputs through the functional units back to registers. This path is provided by this data path. That is why, because this path transforms data from input to output, this is called a data path. And how the data path will transform the data is controlled by the controller. That means, for example, the contents of which register will go to which functional unit at a given time step is controlled by the controller. And then the output of the functional unit will go to which register is again controlled by the controller, as we will see. So, this data path and controller essentially constitutes the register transfer level level specification, structural specification of the design. So, registers are connected to functional units via multiplexers. The multiplexers are controlled by FSM. So, the select lines of the multiplexers will be controlled by FSM, and therefore, the multiplexers will be able to choose which register contents will go to which functional unit at a given time. So, the design at the RTL level, the design is broken into clocked steps. At each step, some registers and functional units are activated, and these activations define the RTL assignments. For example, at time step 1, so suppose we can have RTL specifications like this. At time step 1, perform the following register transfers. So, R1 plus R2 equals to R2 equals to R1 plus R2. So, take the contents of at time step 1, take the contents of R1 and R2, pass it to an adder, and then the output from the adder should be passed back to the register 2 R2. Similarly, also perform the same function, also perform the function R3 plus R4. So, contents of R3 and contents of R4 should be transferred to the adder, and the output of the adder should be passed to R4. So, this also should be done in time step 1. and then at time step 2 similarly other things, other register transfers will be done. So, this is how the register transfer level specification is designed. So, after register transfer level design, we go to the logic level. So, at the logic level what happens? The application or the hardware design is specified in terms of its functional representation. So, what is the functional representation? As I told you, from the RTL specification, we build the Boolean logic or the Boolean equations and FSMs for the controllers. And then what do we obtain through the logic synthesis phase? We obtain a structural realization of this Boolean logic and FSMs in the forms of gates and flip flops, and this is called the gate level netlist. So, what are the important functions that are done? So, we do a state encoding, we do state assignment for the FSM, state encoding and state assignment, and then we form the Boolean equations, and after we have done the Boolean equations, we do logic minimization, both 2 level and multi-level logic minimization is performed to obtain optimized Boolean logic, and then this optimized Boolean logic is transferred to its gate level netlist through the synthesis phase. These first 4 stages of the design is called the front end. So, architectural level, the RTL level and the logic level. So, from the application level if we come, so from the application level, the architectural level, the RTL level and the logic level, these are the front end of the design, and then comes the back end, which is this the circuit level, the physical level, the fabrication level and the packaging. So, these are the back end of the design. So, after the gate level netlist is obtained, we told that we do a technology mapping and we obtain the corresponding transistor level design, which is called the circuit design. And various types of architecture, mainly three types of architectures are possible for the logic design, meaning the logic design can be mapped to the circuit level in 3 types of architectures. So, it can be mapped in terms of FPGAs. So, the logical representation of FPGAs is a set of gates and their interconnections which may be programmed to obtain the desired logic. We can have full custom design where we have fully customized functional blocks. We can also have semi custom design where we have a set of standard cells, and the interconnections among these standard cells needs to be routed to obtain the functionality that we want to have. After circuit level comes the physical level design. At the physical level, the circuit blocks with their real estate requirements and interconnections are specified. So, once we have the transistor level design, we have a fairly good idea as to what will be the area taken by this design on the FPGA floor. Okay. So, then once we have an idea of the amount of space that it will take on the FPGA floor, we have its real estate requirements estimation. And when we have the real for the different types of so the circuit will have different say gate blocks, and each blocks of gates for different connected functions, and each such connected function will have its real estate requirements known once we do the technology mapping and do the circuit level design. And then once the real estate requirements are of these blocks are known, we also know in addition to the blocks the interconnections among these blocks. So, the blocks and their interconnections together specify the functionality, right. So, once the real estate requirements of the blocks themselves, which are for the circuit blocks themselves and their interconnections are known, we represent them again as graph like structures called netlists. And the output, what do we obtain as output from the physical level design? We obtain a geometric layout of the circuit elements and their interconnections. Okay. So, we will have so after the gate level design is done, at And after the gate level design is done, we obtain the circuit level, we obtain each block of circuit, and for each block of circuit we have obtained the real estate requirements, and these, so these will be the circuit blocks A, B, C and D, let us say. These are the circuit blocks, these are the circuit blocks, and the interconnections among these circuit blocks are also known. So once this is known, we can have a layout like this. So we will have a layout, like this. Now this layout is this is what is the geometric layout, and is the output of the physical level design. Such a geometric layout is the output of the physical level design. Now once we have a layout like this, this layout can be fabricated, on the silicon wafers, and once we have the fabricated silicon wafers, it must be packaged into chips at the packaging level. Now after we had this overall hardware synthesis steps, after we have an overview of the overall hardware synthesis steps, we will take a deeper look into architectural synthesis. That is the step that takes the design from the architectural level to the RTL level. Okay. So we said that at the beginning of the architectural synthesis step, we will have a set of concurrently communicating processes, and these concurrently communicating, each such concurrently communicating process will be represented in terms of a sequential program model, and the tool or language that is commonly used for hardware design in this sequential program model is Verilog, VHDL, etc. So this so the program for each process, each communicating process will be specified. Now once this program, the Verilog VHDL description is known, we have another program called the design analyzer, which transforms this specification into a control and data flow graph representation, or CDFG representation, which we will look at what it is. This control and CDFG control and data flow graph representation is then transformed into the FSM controller and data path at the RTL level through a set of processes called scheduling, allocation and binding, okay, which we will also look today. What are they? Yes, architectural synthesis is also called high level synthesis, and the input behavioral model can be abstracted as we said, threaded concurrent communicating process modules, and these are the modules M1, M2, M3, M4 are 4 concurrent process modules, and they represent the set of operations and their dependencies. Process modules have interfaces to other blocks and the outside world. So these may be connected to the outside world, these are connected to other blocks. Now what is the output? So the input was a specification like that, and what do we get as output at the RTL level? The output is a block structure which is represented as, we have a set of register banks containing data, and the data in the register bank are transformed to a set of functional units through an interconnection network of buses, and the output of the functional units are further transferred back to the register banks. Okay. So we have a data path consisting of register bank, functional unit bank and interconnection network, and we have an FSM controlling all the data transfers within the data path. This is the output. So now let us take an example. Let us say that we have a set of statements. Let us say our VHDL Verilog statements, some high level language set of statements are here. E equals to A plus B, G equals to A plus C, F equals to C plus D and H equals to D plus F. These have to be implemented in terms of a hardware circuit. So, we have to do a hardware synthesis corresponding to this small example high level code. Okay. Now, first this code is transformed to a schedule like this. This schedule has two time steps T1 and T2. How this transformation is done we will see, and it transfers and it transforms it in this way. So, firstly if we take the first statement, we see that A and B are passed through an adder and the output generated is E at time step 1. And at time step 2, because E is generated at the end of time step 1. So, at time step 2 what we have is that this E and A are then added, this E and this A are then added in this adder and the output G is produced at time step 2. Similarly, C and D, statement 3 here, C and D are passed through the adder and this output F is produced, and at the next time step F and D, so F and D are added in this adder and the output H is produced. Okay. So, this is the schedule of operations that we have, and what is the kind of RTL level representation in terms of the data path that we realize. So, we store in R1 A and we store B in R2, and then we pass it to adder 1 and the output of adder 1 goes back to R2 and E is produced, and after E is produced, E and A is again added in adder 1 and the output G is produced, which is stored in R2. Okay. Similarly, for the second adder here, for the second set of statements 3 and 4, for statements 3 and 4, these two statements, what we have is the following. We have C in R4 and D in R3, and these two are added in adder 2 and the result is passed back to R4 which is F. F and D are then added again, F and D are then added in a register in adder 2 at time step 2, and the result is stored back in H. Now, we will look at this example in a bit more detail to understand what are the sequence of control signals that are generated, so that the required timing can be ascribed to it and the register transfers correctly do happen for the example that we have here. So, let us say we have the same set of 4 statements and we have the schedule T1 and T2, this is what we have. And how is this implemented? Firstly, we have 4 registers. Okay. We have 4 registers R1, R2, R3, R4, and initially in this one is R1, R2, R3 and R4. So, initially we have A in R1 say, B in R2 and B in R2, and let us say C in R3 and D in R4. Okay. Now, we said that and let us say the functional unit, we have 2 function units, one of them is adder 1, this is say adder 1. We said that the input to the adders are connected through muxes. This one is mux 1 and let us say this one is mux 2. This one is mux 2. So, this one is one input to the adder, this one is the other input to the adder. And we also said that the muxes, the registers will be connected to the functional units via muxes. So, R1 will be connected to this one, R2 will be connected, R3 will be connected and R4 will also be connected. Okay. Similarly, for the mux 2 also the same thing is going to happen. Okay. Now, mux 1 is, let us say, controlled by two select inputs S01 and S11, and mux 2 is also connected through two inputs S02, two select inputs, and S12. Okay. So, these are the two select inputs corresponding to mux 2, and say that the R1, this input, this one is input I1 of mux 1 and this one is input I4 of mux 4. So, I1, I2, I3, I4. I1 is selected when the select inputs are 0, 0. So, R1 will be selected when the select input is 0, 0. R2 will be selected when the select input is 0, 1 for mux 1, likewise. Similarly, for mux 2. So, what we want to say is here is that mux 1 will allow the contents of R1 to pass to adder 1 if the select inputs are 0, 0 corresponding to mux 1. Similarly, we also have a demux. We have a demux at the output, and that will also be controlled through select inputs, say S03 and S13. Okay. And it will have 4 outputs going to, say, R1, R2, R3 and R4. Okay. Now, to implement this operation, this operation E equals to A plus B, let us say that what we want is that the output E should be stored in register R2. Why? Because the input this data in B, this data B is no longer required after time step 1. However, the data input A is required again at time step 2. So, so there is no problem if B is overwritten by E at the end of time step 1. So, now our controller, the specification of our controller would be actually a counter which has two states, and this one is time step 1 and this one is time step 2. So, our FSM is a counter with 2 steps, and the outputs will be, if when it is at time step 1, it will produce the outputs. What will be the outputs? The outputs will be, for time step 1, the outputs will be S01 equals to 0, S11 equals to 0. Okay. And for mux 2, so why is S01 equals to 0 and S11 equals to 0? Because at time step 1, we want the input in R1 to come here. We want A to come here at time step 1. So, therefore, this will be selected. For R2, for the other input of adder 1, we want the value of R2, which is B, to come into the other input of adder 1, and that will be done how? That will be done by having S02 equals to 0 and S12 equals to 1. Why? Because this corresponds to the second input I2 of mux 2, and I2 of mux 2 will be selected when the select inputs are 0, 1. So, at time step 1, R2 the contents of R2 can go to adder 1 if select inputs are 0, 1. And after that, we have said that let us say this one is the output 2 of the demux, O2 of demux, and we want the output 2 of demux because it goes to register 2. We want the output 2 of demux to go to meaning that this to be selected. We want the second output of the demux to be selected, and therefore, at T1 the select inputs S0 3 equals to 0 and S1 3 equals to 1 should be selected, because when the demux select inputs are 0 1, the second output of the demux will be selected, and the output E will be correctly passed to register R2. Similarly, same thing will happen for the other adder. So, I have not drawn the full, there will be another adder 2, and for that it will have again the mux inputs mux 3 and mux 4, and it will similarly have inputs from the 4 registers, and it will appropriately allow correct inputs to pass, and it will have another demux, and each of them will have select inputs, and also the functional units can have activation inputs, and registers can have load inputs as well. So, these inputs can also be controlled by the FSM. So, the FSM essentially will select all the correct control signals which are the select lines, load inputs, activation inputs of functional units, etc., and it will correctly activate correct data transfer from correct registers through the correct functional units through the correct demux outputs back to the registers. So, this will be controlled by the FSM controller. So, these will be the set of control signals that will be output at state 1 of the controller. Okay. This is how the design will be realized and controlled. Now, when we have seen the architectural synthesis overview, we will see the steps in a bit more detail. So, at the end of as we said at the beginning of the architectural synthesis step, what we have are concurrent communicating processes, and each process is a high level language program, let us say. And then this high level language program is transformed by the design analyzer into CDFG or control and data flow graph. So, first we look at what a control flow graph is. So, first step in high level synthesis is the decomposition into basic blocks and generation of the master controller. Now, what are these? So, each module is parsed and its flow chart is extracted. So, the program that we have of each concurrent communicating process. So, each process is a program, and for that process we obtain the flow chart, and from that flow chart we obtain the control flow graph. So, what is this control flow graph? Each node of the control flow graph is a basic block. So, what is a basic block? A basic block is a piece of sequential or straight line code with a single entry point and single exit point. So, we will look a bit more deeply into what a basic block is in the next slide. And then once we have disintegrated the entire functionality in terms of its basic blocks and interconnections between these basic blocks, realizing a control flow graph, we have a master controller. We can generate a master controller for this program. So, what will be the master controller of this program? The master controller is designed from the CFG, and the states of the master controller are basic blocks themselves, and the transitions are same again as the CFG. So, now we see how a particular high level code, a Verilog or a VHDL code, we take an example of C here. A C code can be disintegrated. So, we will take the high level code and transform it into its CFG. So, for CFG, as we said, first we have to find out the basic blocks. So, this program over here has 4 basic blocks, B1, B2, B3 and B4 and B4. And how are these basic blocks obtained? See that the first 4 lines of this high level code form the first basic block. Why? Because this is a piece of straight line code which has single entry point and single exit points. Once the program control enters into the first statement w equals to 0, there is no other way that it can exit other than the last after the last statement. So, once w0 is executed, once w's control enters into w0, we know that up to the if statement it is always going to be executed. So, if w0 is executed, then x equals to x plus y must be executed, y equals to 0 must be executed, and if x greater than z, this condition check must be executed. Now, after that the control breaks. So, we do not have a straight line piece of code anymore, and we have 2 exit points from out of this basic block. Why? When the if condition is true and the other when the if condition is false. Now, we have said when the if condition is true, these 2 statements are executed, which is again a straight line piece of code, and this forms basic block 2, and the other basic block is y equals to 0 z plus plus. This is again a straight line piece of code, becomes basic block 3, and finally, after the join we have another statement which forms the last basic block, because this one contains only one statement with a this is the only straight line piece of code that we have for this basic block. Now, what is the structure of this control flow graph? We enter the control flow graph. We first go into basic block 1. After executing basic block 1, we either go into basic block 2 or basic block 3, and then we have basic block 4. After the execution of basic block 4, we exit. So, this is the control flow graph representation of the high level program that we have here. So, in the first step in architectural synthesis, the input program is transformed. So, each concurrent communicating process is transformed to its corresponding control flow graph. After the control and data flow graph is obtained, we schedule operations within each basic block. So, from the control flow graph, we now go within each basic block. And we say that all operations in a basic block may in principle be performed in a single clock cycle. What do we mean by this statement? Let us consider the example that we had just seen a while back. So, we had this A, B, E, F. So, we had this A, B, E, F. And we said that we had done it previously in 2 clock cycles, T1 and T2. So, could we have so that required 2 time cycles, but we are saying that all operations in a basic block may in principle be performed in a single clock cycle. Could we have done this in the same clock cycle? With the resource constraints that we had over there, we could not have done it. Why? Because we were having only one adder and we had only 2 registers. However, suppose if we had 4 registers R1, R2, R3, R4, okay, and we could say something like this. And if we have 2 adders, adder 1 and adder 2, then we could say something like this. We could say that transfer A this one, okay, and then this output let it go into E. This output may in parallel may go into E, and the output E comes here, and then the output goes here. Now, if we do not have let us say resource constraints like this. We have 4 registers, possibly we could have done it with 3 registers as well, but we needed at least 2 adders, and we have 2 adders. Then what is the advantage do we have? So, A and B A and B passes their outputs no matter when. We start the time step 1 and everything is done in time step 1. How? At the beginning of time step 1, A and B is transformed quickly into A1 and the output is produced, and the E goes into register 1, and then the output this output from this register goes into A2, and finally the output of A2 goes into this register. Okay. Now, what is the constraint here? Constraint are the delays of these registers and functional units and the muxes and demuxes that we have. Now, if the delays, if the summation of this, if we have a clock cycle which is greater than the summation of the delays of these registers, muxes, functional units, etc., then we basically, after the start of the time cycle, we are waiting for a sufficiently long time, and we will see that the output has correctly come into, let us say if this is register output, the output has correctly come into register R4. If we have waited for a sufficiently long time, such for a long time, that a time duration which is more than the cumulative delays of the registers and the functional units and muxes and demuxes which come in the data path processing. Okay. So, we are limited by the delays of the resources, but we do not have any constraints on time because we do not have any resource constraints. However, if we have this sort of a design in which we are reusing this adder, we cannot do it in a single time step. Why? Because we don't know, we need to have a crisp time at which we will have this E value output, and this output will be stored in a register by the end of time step 1, so that this output, we will have a stable output at the beginning of time step 2, and we will produce this F. Okay. So, otherwise we could have a corrupted result, because the output E will be produced and this output will go back to the same functional unit, and it may interfere with A and B, which were the previous contents. We could have several problems in there. However, if we have a sufficient amount of resources, we have no problem in implementing this whole thing in the same clock step. Okay. So, therefore, if we can do all operations ideally in a basic block within the same clock step, but the problems are unacceptable hardware cost and delays. So, unacceptable hardware cost means we saw that we need a lot of hardware to implement it in the same clock step, and delays, we saw that we need more delays. We have to wait for a sufficiently long time for all the delays of the resources to be taken care. Okay. So, the problems are unacceptable hardware cost and delays. So, what is the solution to this? The solution to this is to execute a basic block in several clock cycles. So, the operations of the basic block has to be executed in several clock cycles. This is the solution, and therefore, we need to schedule operations in the various clock cycles within the basic block. The other side of this problem is that, let us say a clock, we have a clock, and this clock will not be exciting only a single basic block. It will possibly be provided, the same clock will be provided to multiple basic blocks. So, we will have a fixed clock size, clock step size for all basic blocks. Okay. If we have that, then if a particular basic block has nothing much to do, it may have to wait. Okay. Or let us say if we have allocated only one operation per clock cycle, then it may have to wait, because these operations are very small, it takes a very small time, and it has to wait after needless to wait before the next operation can be started. So, as a solution to this, people suggested chaining, in which multiple operations may be executed in a clock step if overall propagation delay is less than cycle time. So, what does chaining allows? As we saw that multiple operations can easily be incorporated, but the problems are we need sufficient hardware and sufficient delay. Okay. So, therefore, when can multiple operations be executed in a single time step through chaining? When we have the propagation delay of all the resources in that in those set of operations to be less than the cycle time. If we satisfy this and we have enough resources, then we can do chaining. So, now we come back to what are the steps in scheduling. So, what is scheduling? Scheduling is the assignment of start times to each operation in a basic block, and then after assignment of the start time to each basic block, we generate the controller to direct the operations at each time step within the basic block. Okay. That is also we have seen. Now, we will look at the scheduling steps in a bit more detail. So, we had the control flow graph. In the control flow graph, we had basic blocks. The basic block was a set of statements, one or more statements of the program, and those statements are converted into a data flow graph like this. In the data flow graph, nodes denote operations and edges denote data dependencies. This graph is acyclic and provides a partial order among operations. For example, if we have a basic block such as x plus y into z less than w plus t. So, what we have, this one performs x plus this one performs x plus y star z. See, the dependencies have been adequately taken care. This one performs w plus t, and then this one performs the comparison operation and the output is produced here. So, this is the data flow graph representation of this basic block with its dependencies taken care and the nodes representing the operations. After the data flow graph is obtained, the data flow graph is converted to its operation constraints graph. The operation constraint graph is very similar to the data flow graph, and it shows precedence constraints among operations and with additional source and sink node produced. So, the inputs and the outputs are removed. It only shows the precedence constraints among the operations. The inputs and the outputs are removed, and we add a source node and a sink node. After the operation constraints graph is obtained, we generate schedule. We schedule the operation constraints graph essentially. Okay. So, given area and execution delays of each resource type, we generate the schedule. Multiple options are there for assigning time step to operations. For example, here is the same data flow graph, but two schedules. So, this schedule takes 3 time steps, this schedule takes say 4 time steps. Okay. But we see that here we require 2 adder units in parallel. So, I need 2 adder units to do it. However, here I need only 1 adder unit, because no adder unit, more than 1 adder unit has not been used at the same time step. This adder unit can be reused with say this adder unit or this adder unit. However, these 2 adder units, I must have 2 physical adder units for this addition and this addition operation. Okay. This when this addition is performed, I can reuse one of the adders we used in time step 1, because it is in a different time step. However, in schedule 2, we have all the addition operations in distinct time steps. So, only one adder suffices. Therefore, different schedules will have different amounts of times. So, schedule 1 will have lower delay than schedule 2. So, performance will be better. However, schedule 1 will require more resource and hence will consume more area, will have more cost, etc., than schedule 2. Now, after scheduling comes resource allocation and binding. What is resource allocation? There may be more than one resource type that can execute an operation. Now, we have said that after we have scheduled which operation to do at which time step. Now, this operation has to be implemented on an actual hardware resource. Now, we can have multiple operations for a resource. For example, for the addition operation, we can use a carry look ahead adder or a ripple carry adder. We can have a ripple carry adder or a carry look ahead adder, but ripple carry adder has higher say delay than carry look ahead adder, right. But the hardware again the hardware cost, resource costs are also different. So, therefore, we have to select appropriate resource type. Once the resource types are selected, we need to do binding. That means, the resources operations have to be bound to the functional resources. So, the actual the functions, the operations have now to be actually bound to specific hardware resources. So, we have done an allocation, that means which resource type to use. Let us say we have 2 ripple carry adders now, ripple carry adders, say A1 and A2 are 2 ripple carry adders, and we have operations say AD1, AD2 and AD3. So, we have operations AD1, AD2 and AD3. So, these are the 3 addition operations, and we have 2 adders, ripple carry adders A1 and A2. So, binding would be something like this. We want AD1 and AD2 to be implemented on only A1, and let us say AD3 will be implemented using A3. So, it maps operations to the hardware resources. Okay. That we will use 2 ripple carry adders A1 and A2 was selected in the allocation phase, and this mapping of operations to the actual hardware units was done in the binding phase. So, map operations to functional resources, allocation and binding can be looked at a global optimization problem considering multiple basic blocks. Why? Because then the optimization or the minimization that we can obtain can be much better if we have multiple resources, because the same hardware resource can be reused by some operations in some other basic block as well. So, therefore, this is actually a global optimization problem. Finally, after all these steps are done, the FSM controller for a basic block is inserted into the master FSM controller, replacing the state of the basic block. So, we had the master FSM controller. In the master FSM controller, the states were basic blocks and the connections were the edges of the control flow graph again. Now, this in the master FSM controller, this basic block node will be replaced by the FSM controller that we have generated for this basic block. So, for this particular basic block, to excite different control signals at different time steps and to appropriately conduct the data transfer operations in this basic block, we have generated an FSM controller. This FSM controller is essentially the controller for this basic block, and then it will be replaced corresponding to the overall node of the master controller. Okay. So, these are the steps that we have in high level synthesis. With this, we come to the end of this lecture.